This is SpaceTime, Series 29, Episode 20, for broadcast on the 16th of February 2026. Coming up on SpaceTime, the true composition of the Earth's core, a new look at neutrinos originating from the Sun's core, and what do we now know about volcanoes on Mars? All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
A new study suggests that the planet Earth's core contains up to 45 oceans worth of hydrogen. The findings, reported in the journal Nature Communications, challenges the idea that most of Earth's water was delivered from asteroids and comets during events like the Late Heavy Bombardment around 3.9 to 4 billion years ago. Scientists have long known that Earth's core is mostly composed of hydrogen, a little bit of nickel, but its density isn't high enough for it to be simply iron and nickel. Some other lighter elements must also be present. And one of the primary suspects is a huge reservoir of hydrogen. After all, it is by far the most common element in the universe. Now, in order to work out exactly what's going on in the planet's core, you can't just go down there. So you've got to try and reproduce those sorts of temperatures and conditions in a laboratory. To do that, the authors used a laser-heated diamond anvil, which can simulate the pressure and temperature of the planet's inner core. They then used atom probe tomography to then produce a three-dimensional compositional nanoscale map which identified levels of silicon, oxygen and hydrogen-rich nanostructures formed during quenching. This is what allowed them to determine the percentage of hydrogen in the core. And the results suggest the core contains somewhere around 0.07 to 0.36 weight percentage of hydrogen. And that's equivalent to between 9 and 45 Earth oceans worth of water. Far more than could have been brought in by any asteroid, meteor or comet. This is SpaceTime. Still to come, a new look at neutrinos originating from the Sun's core, and what do we now know about volcanoes on Mars? All that and more still to come on SpaceTime. A new dark matter experiment has provided scientists with a rare opportunity to study neutrinos emanating from the very core of the Sun. Dark matter is a mysterious invisible substance. The big problem is scientists have no idea what it is. Their best hypotheses suggest that it's a type of matter known as WIMPs, which stands for weakly interactive massive particles, which, as the name suggests, involves extremely weakly interacting subatomic particles that only react with normal baryonic matter, that's the stuff you and me and planets, cars, trees, houses and stars are made of, through gravity. But scientists know dark matter exists because they can see its gravitational influence on normal matter, stopping galaxies from flinging apart as they revolve, and bending light from distant objects through a process called gravitational lensing. So there are numerous experiments being undertaken both on Earth and in space to try and unravel dark matter's secrets. One of those is the Lux Zeppelin or LZ experiment at the Sanford Underground Research Facility, 1.5 kilometres down a deep mine shaft in South Dakota. The LZ experiment uses a detector comprising a giant tank filled with some 10 tonnes of ultra-pure, ultra-cold liquid xenon. The idea is if a dark matter WIMP were to pass through the tank and collide with the nucleus of one of the xenon atoms in the liquid, it would cause that nucleus to recoil in the process, releasing a tiny bit of energy. The recoil produces two signals that the detector's photoamplifier sensors would be able to record. One signal is a tiny flash of light. That occurs when the xenon recoil releases a handful of photons. The second is a small stream of electrons, which then subsequently converted into light inside the detector and again become visible at the light sensors. The strength of those signals varies, depending on how much energy the particle deposits, and that gives scientists a means of probing the colliding particle's mass as well as some of its other properties. But the LZ experiment's also been able to pick up signals from another weakly interacting subatomic particle called a neutrino. Neutrinos are the most common forms of matter in the universe, but they're also extremely weakly interacting. In fact, right now, more than 1 billion of them are passing through you every second, and you don't even notice them. They're produced in high-energy events such as supernovae, atomic reactors, and the cores of stars. They come in 3 types, known as flavors. There are electron neutrinos, muon neutrinos, and tau neutrinos. Amazingly, these neutrinos can all transmute from one form to another. So, an electron neutrino can shoot out from the centre of a star, but change and be detected here on Earth as a muon or tau neutrino. The unique neutrino signals picked up by the LZ experiment show that this particular particle originated from the core of the Sun. It marks the first time the LZ experiments picked up signals from this source, in the process setting a new milestone in sensitivity. One of the study's authors was Robert James from the University of Melbourne. James led the statistical analysis that confirmed that the particle was a boron-8 solar neutrino, interacting through neutrino nuclear scattering. Now what this means is it set a new dark matter exclusion limit for masses above 5 gigaelectron-volts. That's roughly the mass of 5 protons. James says the real challenge was modelling the LZ detector in such a low-energy regime for the first time. But he says the results were extremely rewarding, providing a new look at neutrinos from a specific source, the boron-8 solar neutrinos produced by fusion in the Sun's core. The data is a window into how neutrinos interact and the nuclear reactions in the stars that produce them. But the signal also mimics what scientists expect to see from dark matter interactions. You see, the background noise, sometimes called the neutrino fog, could start to compete with dark matter interactions as researchers look for lower and lower mass particles. Reaching into the neutrino fog for the first time highlights LZ's performance with the ability to sense incredibly tiny amounts of energy from individual particle interactions. James says it's the first time that this neutrino signal's been observed at a level signifying statistical significance.
So the LZ experiment is an experiment that's primarily designed to detect dark matter, although as this recent result of ours shows, we can do a lot more with it than just dark matter. But what it essentially boils down to is we've got a very large volume of liquid xenon in what we call a dual phase time projection chamber. So it's mostly liquid xenon. It's about 5.5 tons that we actually utilize. And then a small sort of layer of gaseous xenon on the top. This is all deep underground because we want to basically shield this detector from background radiation, things that would sort of light it up and make it as sort of radio pure and quiet as possible so that we can use it to look for dark matter. And the way it operates essentially is particles will pass through the detector. The ambient radiation, the way we've set it up, should be quite rare, but we still get particles coming through from, radioactivity of the detector components, things like that. In addition to these, neutrinos from the sun, and then intrinsic radiocontaminants in the xenon as well that we can get rid of to some degree, but not entirely. But when one of these particles passes through, it basically lights up the detector. So it produces a signal that we call the S1 signal, and that's basically a light signal. That's just due to the way that xenon responds when you put energy into it. So we detect that with 2 arrays of photomultiplier tubes, which are basically just light detectors at the top and bottom of this liquid xenon volume. And then what we also do is we apply an electric field, and that basically, when you get particle interactions, you get ionization and excitation as well as this scintillation light. And the electric field basically sweeps some of those electrons up into the gas layer at the top. And as the electrons are accelerated through that gas layer, they produce another signal. We call that the S2 signal. And we can basically use the relative and absolute ratios of these 2 signals to tell us something about the sort of particle that interacted. Did it interact with the nucleus of one of the xenon atoms, or did it interact with some of the orbital electrons? And also to tell us a bit about the energy scale of the interaction. And this is really important because it allows us to distinguish between interactions with the nuclei and interactions with the electrons. And we're using this thing to look for dark matter, and the sort of primary design driver of this instrument is something called a WIMP. And a WIMP would be expected to interact with the xenon nucleus. And so that's why having these 2 signals is really important, because it helps us to sort of further disentangle background radiation and other sources of background that aren't dark matter from what a dark matter signal might look like. And we basically just wait for a really long time. We let this detector run, acquire data, and then we look at it and we sort of model the various background backgrounds that we know are there. We put in various models for what dark matter might look like at different masses and different interaction cross-sections. And we use that ideally to look for dark matter. We've not seen any hints of dark matter yet, but in the absence of a dark matter signal, we can use this to sort of rule out what dark matter isn't and start to hopefully eventually hone in on what it is. We know that there's a sort of halo, a galactic halo of dark matter in our galaxy, and we're sort of passing through it. And so dark matter particles are really coming sort of from all directions. And just because of the fact that they interact so weakly with normal matter, we don't expect, for most of the dark matter candidates we're looking for, we don't expect them passing through the Earth to actually have much of an effect. We expect them to scatter so infrequently that they'll just pass straight through the Earth and hopefully, with a small probability, interact in our detector of xenon. But once you look for some more exotic dark matter candidates, those with very large, very heavy dark matter with very large interaction cross-sections, which are also theoretically well motivated in some senses, those do scatter as they pass through the Earth. And so there you do have to take that attenuation into account.
How tough is it to look for something that you have absolutely no idea what it is, really? It's not on the standard model.
Yeah, it's very difficult. I mean, there are viable candidates spanning tens of orders of magnitude, which is absolutely crazy when you really stop and think about it. And so you have to build experiments that work in very different ways to kind of try to fully explore this potential mass range that dark matter could be. So, WIMPs have been historically very well motivated candidates, and there's still a lot of WIMP parameter space that we haven't ruled out yet. And so that's what these big liquid xenon detectors like LZ are designed for. But increasingly, you're seeing these sort of smaller scale tabletop experiments being built, whether you're looking for some coherent interaction from, say, a light mediator with some optically levitated nanoparticle, or whether you're looking at cryogenic bolometers, all sorts of things that are being done to probe that lower mass region as well. And there have been some pretty wild ideas proposed for how we might probe sort of the heaviest potential candidates all the way up at sort of the Planck mass. But I think those are a long way off from being realized. But yeah, you have to get creative, and you have to try new technologies and be prepared to fail sometimes as well.
It's not failing; it's just finding a new limit, a new area that's now ruled out.
Yeah, exactly. Yeah, sometimes when you're trying to communicate this to the public, they come back and they say, "Well, you didn't find anything again. What's the point?" But exactly as you say, you do learn something every time you do this. Yeah. Slowly but surely, we're honing in on what could be dark matter, and I very much hope that in my lifetime we see something a bit more conclusive.
A long time ago, there was this issue of the missing neutrinos, and after a while, we discovered that these were coming from the sun, and part of the LZ detector's work has involved seeing these and studying them as well.
Yeah, exactly. So the missing neutrino problem was a so-called problem a few decades ago where a guy called Ray Davis built an experiment in the same cabin where the LZ experiment now sits. So it's kind of a funny coincidence. But they were looking to detect neutrinos from the sun, and the experiment that they designed was capable of detecting a specific flavor of neutrino, and they basically saw fewer neutrinos than they expected to see. And so for a while, they were quite puzzled. And the solution to this problem actually turned out to be something called neutrino oscillations. Neutrinos are produced in one particular flavor, depending on the decay process that produced them. But then as they sort of propagate through space, they oscillate between flavors. And so when you detect a neutrino, you have a probability that depends on energy of the neutrinos and distance and things like this, and also some fundamental parameters like the mass differences between the neutrinos. You have probabilities to observe those neutrinos in a different flavor than they were produced. And that's just kind of a prediction of quantum mechanics. And so actually the reason why what they were seeing was inconsistent with what they expected was because these neutrinos were oscillating.
So they may start out as a muon neutrino, but then oscillate into a tau or electron neutrino.
Exactly. So the ones produced in the sun are produced as electron neutrinos, and then they oscillate with some probability to become, potentially a tau or a muon neutrino, as you say. And so that problem was kind of resolved. Now, what it is that we found it, is a particularly rare process where we get these boron 8 solar neutrinos interacting directly with the nucleus of one of the xenon atoms in our detector. So when I say boron 8 neutrinos, what do I mean? It refers to neutrinos that are produced from a particular decay in the sun, where positron decay basically of boron 8, which is just an isotope that's present in the sun, and it produces an excited state of beryllium 8 and a positron and an electron neutrino. And we kind of know what the energy spectrum of these neutrinos should be, so what sort of energy profile they should have as they're emitted from solar models and things like that. But there's kind of quite a bit of tension between, so there are different ways that you can set up your solar model. There's what we call the high metallicity solar model and the low metallicity solar model, and they both have different predictions of sort of the amounts of different neutrinos that are produced from these interactions in the sun. And so what we did was we basically provided one of the first measurements of the interaction of those boronate neutrinos with a nucleus through a process called coherent elastic neutrino nucleus scattering, which is a very rare process, and it's actually very similar to the sort of interaction that we would expect a dark matter WIMP, to have with a nucleus. So yeah, the reason why this is interesting is sort of twofold. Number one, it's sort of the first signal that we've measured with this detector that would look very close to a dark matter signal. So it's kind of almost a trial run, if you like, for what a dark matter detection might look like. But secondly, it actually allows us to start to constrain the flux of these boronate neutrinos. And doing that is very important because, number one, as we start to be able to measure these neutrino fluxes, and we'll start to become sensitive to other solar neutrino fluxes as well from other reactions, other nuclear reactions in the sun, will start to become sensitive to some of the other ones as well as we build larger and more sensitive detectors. And that helps us to start to hopefully work towards solution to this solar abundance problem, the high metallicity or the low metallicity. And secondly, it actually allows us to look for potential non-standard neutrino interactions. So if what we observed when we measured one of these fluxes was very different from expectation, could also hint at potential new physics in the neutrino sector. Other experiments also help contribute to this, helps us to start to pin down these neutrino fluxes more and more precisely. And as other experiments start to pin down these fluxes, that actually allows us to become more sensitive to dark matter, because we will eventually get into a regime where, because these neutrino signals look so similar to dark matter, they actually start to become the main background to a dark matter search. And so as other sort of dedicated neutrino experiments start to pin down those fluxes more and more precisely, that allows us to become more sensitive. So there's quite a few different angles to these neutrino physics searches. But what this really is this is sort of the first demonstration of using one of these detectors to do this to a level that exceeded a certain threshold of statistical significance that we start to talk about a significant observation.
Does the flux or the rate of neutrinos streaming out from the sun tell us something about what's happening? Can it be used as an early warning system? Yeah,
so I think you're referring to the supernova neutrinos.
When 1987A occurred, there was this huge flood of neutrinos coming from the progenitor star because the neutrinos flew straight out. They didn't bounce off anything else because they're so weakly interacting, and they hit the detectors on Earth hours before the first photons did.
Yeah. Exactly. So detectors like LZ are part of this thing called the supernova neutrino early warning system. And so there's kind of a whole network of these detectors, and LZ is one of them, that will be sensitive to these bursts of neutrinos if a supernova explosion happened close enough to us. And so, yeah, we're sort of primed and ready to go with that for LZ. We're part of that system. And if we detect a strong burst of neutrinos, then, yeah, all of these sort of parts of this system will spring into action, and tell astronomers, point your telescopes in this direction because we think you're going to see a burst of photons from a supernova soon.
Supernovae are in fact neutrino explosions, not photon explosions. There are so many more of them.
Yeah, detectors like ours that are able to detect the neutrinos.
But at this stage, we can't use neutrino flux to tell us much about what's happening inside the sun.
At the sort of level of detection that we're capable of doing with detectors like LZ at the current scale, no. As we accrue more data, we'll be able to start to say more and more, but it's really the next generation detectors that are going to be large enough to actually start to say useful things about these neutrino fluxes and what might be happening in the sun.
That's Dr. Robert James from the University of Melbourne. And this is SpaceTime. Still to come, what do we now know about volcanoes on Mars? And later in the Science Report, a new study finding how often humans fall passionately in love. All that and more still to come on SpaceTime. A new study has found that young volcanoes on the red planet Mars were far more complex than previously thought. A report in the journal Geology shows that rather than forming during a single short-lived eruption, these volcanoes were shaped by long-lasting and evolving magma systems deep below the Martian surface. To fully understand how volcanoes work, scientists study the volcanic products that erupt on the surface because these can reveal the hidden magmatic systems feeding volcanic activity. The new study, using high-resolution morphological observations and mineral analyses provided from orbit, have revealed that some of the red planet's youngest volcanic systems experienced a far more intricate eruptive history than what scientists had previously thought. One of the study's authors, Bartosz Pajterik from the Adam Mickiewicz University, says a long-lived volcanic system located south of Pavonis Mons is one of the largest of the Martian volcanoes. By combining detailed surface mapping with orbital mineral data, Pajterik and colleagues were able to reconstruct the volcanic and magmatic evolution of this system in unprecedented detail. Pajterik says the results show that during the red planet's most recent volcanic period, magma systems beneath the surface remained active and complex. The volcano didn't just erupt once, it evolved over time as conditions in the subsurface changed. The study shows the volcanic system developed through multiple eruptive phases, transitioning from early fissure-fed lava emplacement to later point source activity that produced cone-forming vents. Although these lava flows all appear different on the surface, they are all supplied by the same underlying magma system. Each eruptive phase preserved a distinct mineral signature, allowing scientists to trace how the magma changed through time. Pajterik says these mineral differences tell scientists that the magma itself was evolving, and this likely reflects changes in how deep the magma originated and how long it was stored beneath the surface before erupting. Because direct sampling of Martian volcanoes is currently not possible, studies like this provide a rare insight into the structure and evolution of the red planet's interior. This is SpaceTime. And time now to take a brief look at some of the other stories making news in science this week with a science report. A new long-term study shows that consuming caffeinated tea or coffee is linked to a lower risk of dementia. The findings, reported in the Journal of the American Medical Association, are based on monitoring of a large cohort of US health workers for up to 43 years. Participants reported their average dietary intakes every 2 to 4 years, and researchers found those who drank more caffeinated tea or coffee were around 10 to 20% less likely to have been diagnosed with dementia over that period of time. The risks seem to be most reduced by having 1 or 2 cups a day of tea or 2 to 3 cups of coffee, with no added benefit for higher amounts. They also found that drinking decaffeinated coffee wasn't linked to any reduced dementia risk, indicating that it's the caffeine which is likely key to the possible protective effects of one of our favourite beverages. Falling passionately in love is one of the most talked about human experiences, celebrated in songs, movies, literature, and in art across all cultures. Passionate love is widely considered the hallmark of romantic relationships and has well-documented psychological and behavioural effects. Yet until now, researchers overlooked a surprising basic question. How many times do people actually experience true passionate love over their lifespan? Well, a new study reported in the journal Interperson surveyed 10,036 American adults, finding that some 14% had never experienced passionate love, 28% experienced it once, 30% experienced it twice, 17% 3 times, and 11% 4 or more times. Overall, experiences of true passionate love were similar across homosexual, heterosexual, and bisexual participants. In fact, romantic love remains a major priority for most people. Data from the Kinsey Institute show that 60% of US singles describe themselves as being very romantic, and a majority endorse ideas like love at first sight and destiny. The Australian Air Force has completed construction of its new MQ-4C Triton hangars at the Tyndall Air Force Base near Katherine in the Northern Territory. Based on the earlier Global Hawk, the MQ-4C Triton is built by Northrop Grumman. Australia's purchased an initial 4 of these high-altitude jet-powered aircraft for long-range maritime surveillance patrols and intelligence-gathering operations. The drones are also equipped for electronic and anti-surface warfare, working alongside the Air Force's manned P-8A Poseidon maritime surveillance aircraft. The $356 million Air 7000 Phase 1B project includes purpose-built facilities to support the MQ-4C Triton, including a new hangar, supporting infrastructure and ground crew accommodation. While based at Tyndall, the Tritons themselves will be remotely flown by pilots at the No. 9 Squadron at the Edinburgh Air Force Base near Adelaide in South Australia. Ricky Gervais' opening monologue at the 2020 Golden Globes probably said it best.
Well, you say you're woke, but the companies you work for, I mean, unbelievable. Apple, Amazon, Disney. If ISIS started a streaming service, you'd call your agent, wouldn't you? So, if you do win an award tonight, don't use it as a platform to make a political speech, right? You're in no position to lecture the public about anything. You know nothing about the real world. Most of you spent less time in school than Greta Thunberg. So, if you win, right, come up, accept your little award, thank your agent and your God, and off, OK?
And after the recent Grammys debacle, who can argue? But now Demi Moore is giving her 2 cents worth on the famous Roswell UFO crash story, claiming the whole thing's real. So a bit of background. The original story involved an alleged extraterrestrial spacecraft slamming into the ground on a farm during a violent thunderstorm, before briefly skipping back into the air and finally crashing hard into the ground in the bank of a dry gully several kilometres away near a remote New Mexican town called Corona. The date was July the 4th, 1947. The next morning, a local farmer named Mac Brazel was inspecting one of his fields to see if the previous night's storm had caused any damage, when he suddenly came across a huge debris area containing lots of wreckage covering the entire paddock. The debris included weird metal beams as light as balsa wood and covered with strange indecipherable writing he described as hieroglyphics. There were also unusual metal panels that could be bent and crunched up only to return to their original shape when released without showing any signs of creasing. Later that day, Brazel visited his uncle, Hollis Wilson, to tell him about the strange debris he had found. Now, Brazel didn't have a radio and he hadn't read any newspapers recently, so he wasn't aware of a nationwide press coverage a few days earlier, on June the 24th, when a pilot called Kenneth Arnold saw what he claimed were 9 silver-coloured unidentified flying discs travelling in unison near Mount Rainier in Washington state, moving at almost 2,000 kilometres per hour and performing manoeuvres well beyond the capabilities of any known aircraft. Now, what Arnold had seen was probably a squadron of military jets. Jets were still very new at that time, and back then they were usually left in their silver colour. Although you'd think that as a pilot, Arnold would have been up to date with the latest aviation news. Coverage of Arnold's report sparked a wave of over 800 similar sightings across America. Anyway, Wilson told Brazel about Arnold's report and suggested that the debris he found on his farm could have been from a flying disc, as hundreds of reports had been made during the 4th of July weekend, and there was a $3,000 reward on offer for any proof. So the next day, Brazel drove down to the nearest big city, which was Roswell, New Mexico, and reported his find to the local Chavez County Sheriff, George Wilcox. Wilcox promptly phoned the nearby Roswell Army Air Force Base, which at that time happened to be home to the 509th Bomb Group of the 8th Air Force, which was the only unit in the world at that time capable of delivering nuclear weapons. The base assigned Major Jesse Marcel and Captain Sheridan Chavette to return with Brazel and gather the material from the ranch. Meanwhile, base commander Colonel William Blanchard notified the 8th Air Force's commanding officer General Roger Ramey of the findings. Then, on July the 8th, for some inexplicable reason, the Roswell Army Air Force Base's public information officer, Walter Hout, issued a press release stating that the military had recovered a flying disc near Roswell. The local Roswell radio station, KSWS, quickly broke the story and relayed the details to the Associated Press, and it was from this that the legend of Roswell was born. Now, sometime later, there were reports that the spacecraft's final crash site in the Dry River Gully had been located by the military and that several alien bodies were recovered and taken away for autopsies. The story goes that the spacecraft and all the wreckage was quickly forensically cleaned up by the military and initially taken to the Wright-Patterson Air Force Base in Ohio before eventually being moved to Area 51 at the Nellis Air Force Base on Groom Lake in Nevada. Later, the Air Force retracted the original UFO story, instead claiming it was nothing more than a weather balloon. However, years later, the Air Force finally admitted the wreckage was actually part of a top-secret experiment called Project Mogul, which used long trains of weather balloons, reflectors and electronic devices to try and use atmospheric acoustics to listen in on Soviet nuclear weapons tests. They confirmed that both the original UFO story and the later weather balloon story were all part of a deliberate government disinformation campaign designed to cover up the true nature of Project Mogul. As for the alien bodies, well, it turns out they were crash test dummies as part of early trials in the 1950s designed to develop jet aircraft ejection seats. But as the skeptic's Tim Mendham explains, Demi Moore is certain that she knows the truth.
Demi Moore was apparently born in Roswell, well after the Roswell incident. That was in 1947. She was born, I think, sort of in the early 60s. But she says that,
not
therefore...
that long after Roswell.
Not a huge amount of years after Roswell, but enough to actually sort of say she wasn't around when it happened, okay? But she says that it's a thing in the air in Roswell, and she said that in her youth, it was something that people just didn't talk about. It was as if it was a secret. Well, it might have been the fact that it had been explained as a crash balloon. In any case, why Roswell, I don't know, because Roswell's about 100 kilometres from where this thing crashed on someone's farm. In a place called Corona, New Mexico. Roswell's a long way away, but this guy took it to Roswell as the biggest town. Therefore, Roswell has claimed it as its sort of incident, even though it didn't happen anywhere near them. I'm not to say that they have museums and they have themed restaurants and things in Roswell.
According to the LORE law, the alleged UFO, and it wasn't a flying saucer, it was shaped more like a stingray, actually hit the ground at a farm near Roswell, skipped on the ground, lost a lot of material, and then flew again for a little while before finally crashing at Corona.
Right, okay. Yeah, that's interesting. What it is that Demi Moore might be promoting a new film that's coming out. She's got a film coming out called Strange Arrivals.
Oh, funny that.
Based on the Betty and Barney Hill abduction story, and she's playing Betty in that film. So there might be an ulterior motive. I'd hate to suggest that. She also makes comments that Roswell has the largest landing strip in America. It doesn't. But apart from that, yep, Demi Moore's an expert on Roswell incidents and UFOs.
That's the skeptic's Tim Mendham, and this is SpaceTime. That's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.